So as we've seen, comparing concentrations that are, 5 times 10 to the minus 5 and 6.3 times 10 to the minus 13, it's difficult to look at those numbers. And so scientists have developed something called pH, which you've probably heard of. Commercials tell us that it's important for our shampoo to be pH balanced. And if you have any experience with swimming pools, you know that the pH of the water in the swimming pool is important for keeping the chemical balance right and keeping it from going green and slimy. So this is what pH means. pH is a function. This lowercase p in front of the h means negative logarithm of. And so we can have pH, we can also have p other things. You could have p calcium or p hydroxide, POH. But we're mostly going to talk about pH. This lowercase p means negative log of. And what this is just a compact way to represent solution acidity. It takes away all the scientific notation and brings it down into numbers that range from 0 to 14. And so it's just much nicer. We need to talk about logarithms for a minute. I'm sure that you all learned about logarithms at some point in your education, but you probably forgot that because you haven't been using it. So if we take a number like 10 to the 4th, the logarithm of 10 to the 4th is 4. If we take 10 to the 9, the logarithm of 10 to the 9 is 9. You see a pattern there? And you can do this on your calculator. In fact, I'd encourage you to do that. You're using the LOG button. So, type in 1,000 and take the log of it. It'll give you the answer 3. 1,000 equals 10 to the 3rd. The log of that is 3. Logarithm answers the question, what power of 10 is this number? And when we look at numbers like 10 to the 4th, 10 to the 9th, we can do those in our head. If it's a negative exponent, 10 to the minus 1, which would be 0.1, the logarithm of that is minus 1. So a logarithm can return a positive or a negative number depending on whether the exponent is positive or negative. Negative numbers are just not so nice to work with. But all these concentrations that we end up with for hydrogen ion concentration, like the concentration at of a neutral solution, the hydrogen ion concentration equals 10 to the minus 7. Well, the pH, if we just take the log of that, it's what?
7.
Well, just the log of 10 to the minus 7. It's going to be minus 7, right? And we don't want a minus. So we put a minus in over here, we multiply it by -1, which makes this into a positive number. And that is equal to the pH. So when we say that pH equals negative log, we do not mean anti-log or anything funny like that. We mean -1 times the log of the concentration. And because this concentration is going to be less than 1 mole per liter for almost everything we're going to talk about, the log of it is a negative number, and then when you multiply by -1, you get a positive number. Any questions yet?
So what does pH balanced mean?
That's a good question. The shampoos, they say pH balanced. Well, the pH is going to be appropriate for putting on your hair. Okay, so most of the tissues in your body have a pH of about 7.4, which is just slightly above neutral. Pure water would be 7. So it's a little bit higher in hydroxide ion concentration. The contents of your stomach are very acidic because your body makes hydrochloric acid in your stomach to help you digest your food. So there are parts of your body that are acidic or basic, but most of your body is fairly neutral. And so you don't want to be putting a shampoo on your hair that's really acidic, or especially one that's really basic, because it'll actually start dissolving your hair. And some soaps were traditionally made by heating some sort of a fat, like bacon grease or lard, with lye from wood ash, which was potassium hydroxide. And if you don't do the reaction right, you could end up with leftover hydroxide in the soap, and the soap could be very alkaline, could be very basic, and that's not going to be good for your hair. So that's what they mean by pH balanced.
So pretty much all cosmetic products are pH balanced.
Yeah, they're all going to be pH balanced. Okay. It's like they came out with this whole fat-free craze, and so now they're labeling all this candy fat-free. Did they change something about it? No. Pure sugar with food coloring and a tiny bit of flavoring was always fat-free, right? They're just pointing that out to you because they think that might make you buy it. So they're just flashing all this stuff around at you. It's really pretty silly. Yeah, they're not going to be able to sell a shampoo that dissolves your hair, right? They might sell a couple of bottles, and then people will make a stink about it, and nobody else will buy it. So it has to be safe, right? So this is great if we have, we can do this just in our heads if this is 1 times 10 to the minus 7. But what if it's something like that last example we did, 5 times 10 to the minus 5 was the concentration that we figured out for the hydrogen ion. Well, what's the log of that? You can't do that one in your head. It's going to be, this number is between 10 to the minus 5 and 10 to the minus 4. And so the log of that is going to be 4 point something. But the way you would do this is you just use your calculator. Now, some of your calculators, like mine, you put the number in first, and then you press the log button. Other calculators want you to press the log button first, and then put in the number. So I put in 5 times 10 to the minus 5, and then I press the log button, and it tells me minus 4.30. I want to make that a positive number because pH is the negative log. We change the sign. And so the pH for this one is going to be 4.30. And so what pH does is it takes this huge range from 1 to 10 to the minus 14. Good luck graphing that, right? 14 orders of magnitude. It's a huge range of concentrations. And it condenses it into 0 to 14 so that you can graph it. And if you know anything about graphing and that aspect of math, it's a good thing. We don't need to elaborate on that. So let's go back to the slides here. So it's a compact way to represent solution acidity. Just makes the numbers easier to deal with. The pH will decrease as the hydrogen ion increases. That's because of that negative number. As you get closer to 1, the number will get smaller. Just a quick word about significant figures. I'm not going to grade you on this at all, but I just want to tell you about this because I find it interesting. There's a lot of chemistry instructors who don't understand how significant figures work with logarithms. But when we're doing pHs, the number of decimal places in the log are the number of significant figures. And so that's equal to the number of significant figures in the original number. And I'll kind of demonstrate that to you as we go along. So the pH range goes from 0 to 14, and pH equals 7 is neutral. Because at pH equals 7, we have the hydrogen, we have the hydrogen ion concentration being equal to 1 times 10 to the minus 7 moles per liter. The log of this number is 7. We change the sign, we get from negative to positive, and we get positive 7 is the pH. That's neutral. If the pH is greater than 7, we have a basic solution. So in a basic solution, the hydrogen ion concentration is less, right? And the hydroxide is higher. So in a basic solution, what's a possible concentration? 1 times 10 to the what? What would be smaller than negative 7? Negative 9. So let's say it's 10 times 10 to the negative 9. So making the hydrogen ion concentration lower, if we do pH on this, what do we get? The log of 10 to the minus 9 is minus 9, and we change the sign, we get plus 9. So for that particular example, the pH is 9. So when the pH is higher, you have a basic solution. When the pH is lower than 7, you have an acidic situation. So let's just do a little example for that one too. What would be a higher concentration than 1 times 10 to the minus 7? Minus 3. 1 times 10 to the minus 3 molar. That's higher in concentration. Higher acid acidic solution. What's the pH then? 3. And I'm not using I told you about sig figs and then I'm not using them. So what I meant about the significant figures is in this number, there are 2 significant figures, the 1 and the 0, 1.0. When we do the pH, this 3 is coming from the exponent. It's not really a significant figure, it's a decimal holding number. And so both of the significant figures come after the decimal point. So pH lower than 7, acidic solution. And that's something I want you to be able to do on an exam. If I tell you, oh, this has a pH of 8.5, is it acidic or basic? It's basic. If the pH is 1, acidic or basic? Acidic. Okay, so 7 is neutral, higher is basic, lower is acidic. So this is an interesting little graph. Here we're seeing the pH scale going from 14 down to 0. And over here we see the hydrogen ion concentration. And we'll notice that a pH of 14 corresponds to a hydrogen ion concentration of 10 to the minus 14. So this is a very low hydrogen ion concentration. Here in the neutral, right in the middle at 7, we have pure water. That's at 7. Your blood is at 7.4. Little bit basic. The pH of your blood matters a great deal, and your body has systems in place to regulate it and keep it in a very narrow range. I think it's like between 7.3 and 7.5. It keeps it right in that really tight range. If the pH of your blood gets significantly higher or lower, you're in trouble. Milk is close to basic, but it is still slightly acidic. But these guys are right in here. Down here, in the more acidic range, at the very bottom here, we've got 1 molar HCl, which is pretty concentrated. Here you've got stomach acid, around 2. Very acidic, your stomach acid. So when you vomit, which none of us like to think about that, but I think it's happened to all of us, you get this really sour, nasty taste, right, and burning sensation. That's because of all this acid that's coming up from your stomach. Your stomach is designed to have acid in it. But your esophagus and your mouth and your teeth are not designed to have acid in them. So just a tip, because I can't help telling people stuff like this. I guess because I'm a mom. I don't know. After you vomit, it's really important to rinse your mouth with water and get the acid off of your teeth. You don't necessarily want to brush your teeth because the acid softens the enamel and you don't want to be scrubbing at the enamel, but you should always rinse your mouth with water after you throw up. So stomach acid's right down there. Lemon juice, vinegar, very acidic. Question?
Yes. How about something like antacids? Is that going to be more like a neutral, or is that going to be more basic to neutralize the acid?
An antacid is going to be a base, okay? And some of the bases on here we see are like ammonia. Ammonia is basic. 1 molar sodium hydroxide is basic. Bases tend to be very destructive to tissue. And so then you may say, well, how can we swallow an antacid, which is going to neutralize the acid in my stomach, and do that without hurting my mouth and my esophagus? And that's because they are very weak bases. They don't ionize much. And so you can chew them up and swallow them, and they're not going to really react or do anything until they encounter the acid in your stomach. And when we need to take an antacid, there's lots of different reasons for that. You need acid in your stomach, but you don't want acid reflux, which is where the acid starts to come up your esophagus. That tissue is not designed to be in contact with acid. Sometimes your body's overproducing acid, but sometimes there's other problems. When a woman's pregnant and the baby's getting bigger and putting pressure on all kinds of things inside, sometimes you can have some really horrible heartburn. And it's not because your body's making too much acid, it's because there's this big old baby in there pressing on your stomach, and everything kind of loosens up, and that valve is not sealing like it should, and so it allows stuff to come up. So there's all sorts of different causes for needing to take antacids. But yeah, they are bases. They're definitely bases. Any other questions? Most of the, well, pretty much all the foods we eat would fall into the close to neutral or acidic range. And so one of my pet peeves is all these alarming things that go around on Facebook and email and the internet and stuff. They're like, oh, the pH of Diet Coke is like 2 and it's horrible and it's going to dissolve your insides. Your stomach's full of hydrochloric acid. What's the big deal? It's not a big deal. And that's why I think everyone should have some knowledge about chemistry. And you can look at these things and say, oh, I'm not so sure about that. Maybe, I'm either just going to blow it off, or if I'm really concerned, I'm going to look into it some more. But people get really bent out of shape about stuff, and a lot of times it's just dumb. Just not factual. So let's look at these. Let's calculate the pH for each of these solutions. So this first one, 1 times 10 to the minus 4th molar hydrogen ion. I think we can probably do this one in our heads now, right? The pH is going to equal the negative log of the hydrogen ion concentration. So we look at this number and we say the log of that number is the exponent, minus 4, and we change the sign and it becomes plus 4. But also do it on your calculator. So 1 times 10 to the minus 4, and you have to enter that scientific notation number in a way that your calculator understands that it's a single number. And then change the sign and you should come up, your calculator will show you 4. This number has 2 significant figures, so we should add 0.00 at the end. pH does not have a unit. This concentration is always in moles per liter, and then when we take the log of it, it doesn't have a unit. Your calculator's cooperating with you? No? Okay. So it's really important to make sure that you understand how your calculator wants you to type the things in. So now, let's do this one. What is wrong here? What's different compared to what we were given in A? It's not in scientific notation, and they gave us the hydroxide ion concentration. We can't use the hydroxide ion concentration to calculate the pH. What can we do? Can we calculate the hydrogen ion concentration? Yeah. So this one's a little more involved because we have to use this equation, hydrogen ion concentration times the hydroxide ion concentration is equal to 1.0 times 10 to the minus 14. And I will give you that equation on your table of useful information along with the pH equation. You just need to know how to use them. So we need to solve this for hydrogen ion concentration, so we'll divide by the hydroxide. That'll cancel out. We'll do the same thing on the other side. And so the hydrogen ion concentration is going to equal 1 times 10 to the minus 14 divided by what they gave us here, 0.040. So 1 EE minus 14 divided by 0.04. That is 2.5 times 10 to the minus 13. That's the hydrogen ion concentration. Now we take the negative log of that. And we can't do that one in our head. But the pH will end up being 12.60. Your calculator's cooperating? There's this relationship between hydrogen ion and hydroxide ion. It's a little bit like, let's see if I can draw up here. It's a little bit like, here's a pole and you've got a rope that you threw over the pole. And if you pull this end down, what happens to the other end? It goes up, and vice versa. When one goes up, the other goes down. And they are tied together like that. And this expression, hydrogen ion times hydroxide ion equals 10 to the minus 14, is what allows us to find what the other one is. Pardon me? It's an inverse relationship. If one goes up, the other goes down. Yep. They're inversely related. Any questions? Yes?
How did you get a 12.60?
How did I get the 12.60? I took this number, 2.5 times 10 to the minus 13. This is the hydrogen ion concentration. And I put it into this equation. So I took the logarithm of it and changed the sign. You're welcome. And if we look at this exponent, without this coefficient at the beginning, we would expect the pH to be about 13, right? Close to 13. And it is. It's close. It's 12.6. We just can't predict in between the 12 and the 13 because it's a logarithm. Yes?
You know who came up with 1 times 10 to the minus 14? Like the scientist?
I do not know who originally came up with scientific notation.
No, with that particular number for this.
Oh, with the 1.0 times 10 to the minus 14, they've measured that. Many people have measured it. I'm sure there's one particular person who got credit as the first publication, but we don't generally remember his name, which is kind of sad. That's a good question, though. It seems like it seems to me like too simple of a number, doesn't it? It's like, oh, it should be messier than that. 1 times 10 to the minus 14, really? It is what it is. You know, not everything is complicated, I guess. The ideal gas constant is, 0.08206. That's messy. Any other questions? Well, what if we know the pH and we want to know the hydrogen ion concentration? The pH of a solution is 5.85. What is the hydrogen ion concentration? Well, we know that pH equals negative log of the hydrogen ion concentration. We need to solve this equation for hydrogen ion concentration to answer this question. This is not a level of algebra that I expect of Chem 10 students. I'm going to do it for you really quick, but if it doesn't make sense, don't worry about it. So in solving this, I'm first going to get rid of the negative sign on this side. I'm going to multiply both sides by a -1, and so this side becomes positive and that side becomes negative. Then I need to get rid of log. Getting rid of log is not a simple matter like dividing by log, because it's a function and we have to do the opposite function. The opposite of logarithm is 10 to the x. And so what I'm going to do is I'm going to take each of these sides and make it the exponent of 10. I'm going to have 10 to the log of the hydrogen ion concentration. Well, 10 to the log of something is just equal to the something. And so that's where we get this equation, which I will also give you on the exam. The hydrogen ion concentration equals 10 raised to the power of negative pH. So whatever the pH is, here it's 5.5. We're going to say 10 to the negative, whatever that pH is, 5.85. Now that's not a normal notation, is it? We've always had exponents on our 10s that were whole numbers. So we need to use our calculators to put this into a more normal form. So the other function on your log key on your calculator is 10 to the x, because those two functions are opposites of each other. One does, the other undoes. So depending on how your calculator works, on mine, I have a TI-30XA. I put the number in first, so I enter 5.85. I change the sign and make it negative, and then I press the 10 to the x button. And the number it gives me is 1.4 times 10 to the negative 6. On other calculators, you may need to press the 10 to the x button first, and then negative 5.85, and then press the equals. You should come up with the same number. I rounded this to 2 significant digits because there's 2 significant digits in the pH. Is your calculator cooperating? Does anyone need me to look at it? Again, when we look at this, the pH 5.85, that's close to 6, right? It's between 5 and 6. And this number is between 10 to the minus 5 and 10 to the minus 6. So even though we can't predict exactly what it is without using a calculator, we can look at our answer and say, yeah, that's ballpark. I probably did it correctly. Any questions? There's a bunch of equations, huh? I want to show you something cool that's kind of a shortcut. So we learned about this one. Kw was 10 to the minus 14. The hydrogen ion times the hydroxide ion concentration always equal that number. Well, if we take the log, and you don't have to understand this part. I'll tell you when you have to understand again. What we can do is we can take the negative log of both sides of this equation, So on this side, we get the negative log of kW. On this side, when you take the log of numbers that are multiplied, you add them together. So you've got the negative log of H plus minus the log of OH minus. The negative log of something is P, that thing. So P kW is the same as negative log of kW. Negative log of H plus is pH, and negative log of OH minus is POH, the negative log of the hydroxide ion concentration. Because kW is 10 to the minus 14, pKW is 14. So this is the part you need to understand. This is a really nice little equation that relates pH and POH. They always add up to 14. And that may seem mysterious to you, and that's okay. It has to do with logarithms. When you dig into it and understand logarithms, it's really cool, but I don't want you to mess around with that unless you're interested in it. So that's a useful little equation that I'll also give you. These are the same things down here, but now the question has changed. Calculate the POH. P is a function that means negative log of. So POH is equal to the negative log, instead of hydrogen ion concentration, the negative log of the hydroxide ion concentration. The one down here on the bottom is the easiest one, right? Because they gave us hydroxide ion concentration. So here, POH will equal the negative log of that number. So the POH is 1.4. I just took the negative log of 0.04. Any questions about that one?
Would it be 1.40 with significant figures, or would we keep it 1.4?
Oh, you're right. It would be 1.40. Yes. Because only the places after the decimal point count. Thank you. This number has two significant digits, the 4 and the 0. And here we don't count this 1. We're just counting those. Now this guy, we could do it where we use the hydrogen ion times the hydroxide ion equals 1 times 10 to the minus 14. Or we could calculate the hydrogen ion concentration and use pH plus POH equals 14. Personally, I think that approach is more simple. So let me show you something really quick here. Just need a blank spot. There's this circle. We've got hydrogen ion concentration, and from that we can calculate pH. From pH we can calculate POH. From POH we can calculate hydroxide ion concentration, and then we can go back and forth between these two. The relationship here is that KW1. The relationship here is that pH equals negative log of the hydrogen ion concentration. Or going the other way, the hydrogen ion concentration equals 10 to the minus pH. This relationship down here is the simplest. And then the relationship between POH and POH and OH minus is very similar. That's not going to fit. I'll kind of write sideways. POH is the negative log of the hydroxide ion concentration. Don't tip on me. Or hydroxide ion, oh, that's dumb. Hydroxide ion concentration is 10 to the minus POH. So, you've heard of the circle of life. I call this the circle of pH. In that first problem, we're given a hydroxide ion concentration and we're asked to find the POH, which is directly across the circle. It's going to require 2 steps, but you can go to the right and calculate pH and then POH, or you can do it the other way. You can go from hydrogen ion to hydroxide ion and then to POH. Which direction you go is your choice. Personally, I think that this relationship is easier to deal with than this one. And so for that problem, I'm going to take the hydrogen ion concentration, calculate the pH, and from that, calculate the POH. Because the pH and the POH add up to 14. Oops, that's not what I wanted to do. Okay, I don't know. Whatever. I'm having an issue with my program here. So this guy. We have hydrogen ion concentration. They want us to find POH. Let's calculate the pH first. We can actually do that in our heads, right? pH is the negative log of the hydrogen ion concentration, which here is 1.0 times 10 to the minus 4. The log of 1.0 times 10 to the minus 4 is minus 4. We change the sign. This pH is equal to 4. We know that pH plus POH equals 14. So if pH is 4, POH must be 10, right? When it's simple numbers, we can look at it and see it. What if it's not simple numbers? Well, what we're going to do to rearrange this is we're going to subtract POH from both sides of this equation. pH plus POH minus POH equals just the pH, because anything minus itself is 0. And then over here we have 14 minus POH. So that's 14 minus 4. Stop me. I did that all backwards. We're subtracting the pH. Because we're trying to find this. Sorry about that. Like you need help confusing, right? That's not what I'm supposed to be here for. So it's 10. Done enough.